All right, we'll get started here. So you guys did these examples yesterday. We'll do them together now. These two really highlight the idea of the integral that you have to write has got to be algebraically equivalent to the integral that you have, because math. So being able to see those things is really the skill here. Understanding how, like if at any point, you struggled or you weren't 100% sure how our pieces mesh together when we multiply and divide, this one really shows that. What was I going to say? The one thing that I didn't say yesterday that I think is important, and I kind of caught it from some mistakes where people were making. When you write your new integral, you should not be writing the letter x, right? That's important. I didn't say that yesterday. Obviously, didn't do it in any of mine. But the new integral should be 100% u's. That's number one. And then when you integrate, you're always getting u's. So that was another thing that showed up, especially when we were integrating the 1 here. A lot of times we were getting an x, but we're in terms of u, that 1 becomes a u. Okay. So let's take a look at these ones. We decided, and it took a minute. We tried a couple things here. Is u sine x? No, because cosine x being directly multiplied to dx is not in this function, right? There's no just cosine being multiplied against dx, so sine x was not our function. We could not choose 1 minus just cosine x, because that thing is not in our function. This is 1 minus cosine cubed x, and there's no way to get just 1 minus cosine x out of that. So we landed on it being just u being cosine x, and the nice thing about that is du is negative sine x dx. And we do have a sine x being multiplied by a dx in our integral, because multiplication doesn't care about order. So if I just flip-flop these two terms around, I'd legit have sine x dx. So u is cosine x, du is negative sine x dx, and we want a positive sine x dx, so we just made that negative du sine x dx. Perfect. So that means that the sine x times the dx is being completely replaced with a negative and a du. Okay, so the highlighting, like I was highlighting to show that. I have highlighters. If you guys want to practice, if you want to grab some highlighters to do this, you can do that as well. So the sine x dx is being completely replaced with a negative and a du, which means that when I go to write my integral, I'm going to have a negative out front because coefficients come out in front of the integral, and I'm going to end with du because that's where that belongs in an integral. Okay? And then it's just a matter of taking the 1 minus cosine cubed x and replacing the cosine x with u. So we have the integral of 1 minus, let's see if I make this blue just a hair lighter. I'm going to go with this lighter blue here. That's what I want to match my thing. 1 minus u cubed. And again, when I go to the bottom and I'm doing my check, I'm just showing that I'm, algebraically equivalent, not part of the problem, but part of, your thought process to verify that you're correct. I have everything accounted for there, and I have nothing that wasn't there. You can by the colors see where everything came from. Where did the negative and the du come from? Well, negative du is sine x dx, according to our work on the right. Where did the 1 minus u cubed come from? Well, 1 minus was there, and our u was cosine x. That's what I'm writing down on the bottom when I'm writing the algebraically equivalent part, what I just said there. Yep. Morning. Did you stop at attendance? Okay, cool. So now, the parentheses in this case aren't really serving any purpose. So we really do have now just a subtraction problem. We have to integrate 1, we have to integrate u cubed. And when we do that, we end up with, Desmos, apparently, we end up with u minus u to the fourth over 4. I guess those parentheses are important because the whole thing is multiplied by a negative. And then we have a plus c at the end. Pass. Cool. Gotcha. All right. And then it's just our job to backfill this with u equals cosine. And whether we want to or not, it doesn't matter. Distribute that negative. I'll distribute the negative. So distributing the negative is going to make the first part negative cosine x. Morning. Pass? Cool. Thank you. I got to remember to, when I'm done, to change you from absent to present. And then we're going to, again, distribute that negative to give us plus cosine to the fourth power of x over 4 plus c. And again, the thing that we integrated was negative 1 minus u cubed du, which is a negative 1 minus cosine cubed of x times du, which is negative sine x dx. And those two negatives cancel out to give us, and so those two negatives cancel out. I have three things being multiplied. I have these parentheses being multiplied by sine x being multiplied by dx. There's an extra set of parentheses there. I added that because otherwise this looks like a subtraction problem, but this is three things being multiplied. So canceling out those negatives gives us exactly what we started with, which is sine x times 1 minus cosine cubed x dx. Oop, a little bit off. Okay. Again, that bottom line, not part of the problem, part of the thought process. I kind of already did it thought process-wise. Now that's me just showing it so that you guys get yourselves to the point where you can do it thought process-wise. Questions on that one? All right. Number 6, really, like I said, these problems show us how algebra works. This one really highlights how denominators and numerators work. We went through a couple things and we came up with our u equaling 1 minus ln x, which made our du equal to just negative 1 over x dx. And for the algebra of this all, dx works just like a variable. That is no different than having dx over x. Negative, of course, but that dx can slide up into the numerator as well. And that's the stuff that we have. We have a dx in the numerator, and we have an x in the denominator. It's like exactly what we want, minus the negative sign. So same fix as the previous problem. Negative du is what we're going to plug in for 1 over x dx, or even dx over x. Writing it that way just to match how the problem is written. This is the same problem as 1 over that denominator with the dx on the outside. And of course, my u is 1 minus ln x. So writing an algebraically equivalent integral, instead of the dx in the numerator and the x in the denominator, I'm instead writing negative, oops, thought I was orange, negative du. So the orange is completely accounted for. I need something in my numerator, so I'll placehold with a 1. And in the denominator, I have the square root of u. Everything's accounted for. Everything's algebraically equivalent. So now we can integrate. 1 over square root of u is power rule, right? Denominators don't mean ln of. It's only that when the exponent is 1. We have a denominator exponent of 1/2, or an overall exponent of negative 1/2. Neither of those things are an exponent of 1, so this is power rule. I think with square root, you kind of get into this, you do it a couple times and you kind of know it. Whether you're taking a derivative or an integral, you end up with a 2 in front of that square root, which is nice. So this integral comes out to 2 square root of u du. Or, sorry, just 2 square root of u. Plus c, and I know I need the negative. So I need the negative from the front, and I need the plus c. But the antiderivative is 2 square root of u, which is what I was kind of trying to focus on. Cool. And then we just go back and do our thing. So that's going to be negative 2 square root of 1 minus ln x plus c. And again, verifying that everything, I did it with the colors. I'll do it in our work here. The thing that we integrated was 1 over square root of u du. And then going back to the algebra on the right, that's a negative 1 over the square root of 1 minus ln x times negative 1 over x dx. Just like the previous problem, the negatives cancel, the denominators multiply, and we end up with a denominator of x square root of 1 minus ln x. Okay, I just rearrange the order that I multiplied the two denominators in. I can make the numerator dx, or I can leave the numerator as 1 and push that dx out to the side. They're both good. Right. I think that's the last time I'm going to do that part. From now on, I'm just going to do the part where I talk it through, but I'm not going to write it here. If you want to write it here to verify that you're correct, go for it. Until you get to the point where you have this in your head. I can't emphasize how much integrals are not just, oh, I have this thing, I'm going to do this thing. Those integrals are very close, yes? One of them has a numerator of x, the other one has a numerator of 1 with the dx slid into the numerator. U substitution. Take a look at number 1. I think it's the easier one for U substitution. We are looking for, as a reminder from yesterday, something that's in our function, in our integrand, that when I take its derivative, I find that thing's derivative still inside the integral, possibly with a different coefficient. 4x squared works. There are actually 2 ways to do this one. You can do 4x squared. You can also take the 1 along with it and do 1 plus 4x squared. And they will both lead you to the same answer. One of them will just be a horizontal shift of the other. So, like I said, this particular one, because nothing is happening to the 4x squared before the 1 plus is added, you can bring the 1 plus along with it. That's not my right color. I'll change that to, or no, it is my right color, right? I was using blue there. All right. That makes my du equal to 8x dx, which is great because I have an x and a dx. So I just need to get that right-hand side, which that should be in orange, right? Totally lost my colors. No big deal. Du equals 8x dx, which is great because I have an x dx. So to get my right-hand side to show that x dx, I've got to divide by 8. So I'll use 1/8 as that. 1/8 of du is the x dx that I have inside of my integral. Okay. All right. My u is 1 plus 4x squared, highlighted. So my equivalent integral is, instead of x times dx, which I have, I'm putting 1/8 out front and du at the end. Or I could have actually put it in the numerator. They're both fine. Yeah, in the numerator or at the end. I'm going to leave it at the end because it's there. So I'll put a 1 to placehold over u. Yeah, that's it. Okay, the idea here is we should end up with a must know. 1 over u is a must know. ln absolute value of u. Yep. So this is ln absolute value of u 1/8 plus c, which means our answer is 1/8 the ln of 1 plus 4x squared. 1 plus 4x squared, is that ever negative? No. I'm going to use parentheses then. Hey. Yeah, we don't have any. Hey. Yeah, we don't have any.
It was like $5 each, but we could really do that.
Yeah, we really could do it. All right. So yeah. So that is an example. That is an example where something has turned into the situation where you do the ln of something. Nobody is marking you putting absolute value bars on something like that on an open-ended. They can't put both as answer choices in a multiple choice because they were both correct. So if the bars go away in a multiple choice, you just have to think to yourself, is that because the thing inside them was always positive? And that's really all it comes down to. Questions on that? In question 2, can I make u 1 plus 4x squared? I can't, because I don't have an x dx to highlight in orange. What must-know derivative, what must-know integral does this most look like? Not tangent, but arctangent, inverse tangent, right? Yeah, inverse tangent. And that's what these ones are. If you have the must-know for any of them, tangent, sine, you probably won't see it for arcsecant because arcsecant is weird for like 5 or 6 different reasons. It is the weirdest of our derivatives, and books don't even agree on certain technical aspects of secant, so they usually leave it off. If you see the must-know, or what looks like the must-know, with the exception of the coefficient in front of your x, these kind of have their own little process to do here. It's a little bit, we could do it the same way, but I like to do it this way. What we want is, we want this to be u squared, right? Because if that said 1 plus u squared, we'd be there, right? So I usually first, if I know I'm working in the arctan or the arcsine, I just say u squared equals 4x squared. I'm a little bit ahead of myself. I want that to be 1 plus u squared. So why not make u squared equal to 4x squared? That works because then u is 2x and du is 2 dx. Those should be in orange. And I've got what I need except for a coefficient. I have the dx. So all I need to do, what do I have to do with the du equation? Divide by 2. So I'll write that 1/2 du equals dx, and I'm ready to go. So we'll do integral. We'll do 1/2. To match the original integral, I will write du in the numerator. Again, not right or wrong either way. My denominator is 1 plus 4u squared. No, not 1 plus 4, 1 plus u squared. Sorry, yeah, that we didn't fix anything if I'm writing 4u squared. 1 plus u squared, meaning that my antiderivative is arctan of u. So I'll just write 1/2 arctan of u plus c, which means we've got 1/2 the arctan of 4x squared, 2x. Be careful with that one. I almost made the mistake. It is the arctan of u. So the must-know integral has u squared in its denominator, and that is the derivative of the arctan of just the variable, which means that u equals 2x, which probably should be in blue, is what you're putting in there. Another easy spot on this is usually that coefficient is going to be a perfect square, right? 4, 9, 16, 25, so that this line doesn't give you an ugly square root. Not that it has to be, but I don't know, just kind of a something to watch for. Alrighty. Okay. So in each of those situations, if you worked backwards to check to see that the thing that you wrote as the antiderivative, if you took its derivative, you'd get back to where it started from. We were reversing the chain rule. You would do the chain rule when you were finding that derivative. This is another situation where U substitution is handy. And this is a second situation where U substitution is handy. And we're not actually doing that. Like if you then took the derivative of the thing, it wouldn't be the chain rule that you were actually reversing. When we use this method, we have usually two linear terms being either multiplied or divided. So that's what we have. That's the identifier for this type of problem. X plus 1 is linear, and we're multiplying it by the square root of x minus 1. X is linear, and we have 2x minus 3 to the 5th power. Usually, one of them is kind of, just a simple linear term, just x plus 1. And the other one has something being done to it, raised to a power. 2x minus 3 being raised to the negative 5th power. X minus 1 being raised to the positive 1/2 power. What we want to do here is, our goal is to simplify this guy so it is just U. So the one that has something being done to it, that's what we want to be our U, because then we can actually do algebra that works. There is no good algebra to do with x plus 1 times the square root of x minus 1. I can't push that x plus 1 in there in any way, shape, or form. There's no good algebra to do here because it's in the denominator, because it's being raised to the 5th power. I can't split this up into a 2x and a minus 3. But if in both cases I make the two binomials that have something being done with them into my U, we now have algebra that we can do. So I'll show you how to do that in these two examples. So you're going to make, in both of these cases, U equal to just the linear guy. So U equals x minus 1. I'm going to leave a spot because we actually have to do a couple algebra things over here on the side. Correct. The thing that has something being done to it. X minus 1 is being raised to the 1/2 power. That's what you want to set your U as. I want that to say square root of U instead of square root of x minus 1. I don't want a binomial anymore. I want a monomial. In the thing where things are happening. Square root raised to the 5th power. That makes my du dx. That's nice. There's nothing to do with that one. Du is dx. I can write them interchangeably. The thing is, I need to know I know I can make this U, but I don't need to know I don't know what to make x plus 1. That's not hard. Let's do green. Well, all I'm going to do is I'm going to transform x minus 1 into x plus 1. So what do I have to do to x minus 1 to make it x plus 1? Add 2. Add 2 to both sides. So I have this third piece, U plus 2 equals x plus 1. Yep. So there we go. So now we are going to get an algebraically equivalent integral. Shock. And that algebraically equivalent integral is going to be the quantity of U plus 2 times the square root of U. Yep, should have been. Yeah, du, thank you. Yep, colors. Square root of U, and then du. Cool. Algebraically equivalent, the colors show it. That U is really just U to the half, so let's fix that in line instead of writing a new line. Dot there just because of how much space I left. But now I have something that I can distribute. Yep, that u can be distributed in, and I have the integral of u to the 3/2 plus 2u to the 1/2 du. Sure. Usually the way we do it with integrals is they work in a way like parentheses. So the integral starts with the symbol and ends with the du, which is why we usually leave it there. I mean, obviously when we put it in the numerator of a fraction, it's kind of ending it as well, but just for notation wise, we know that the integral stops when you hit the d whatever, and that's kind of where we go. Okay. Yeah, unless you're in Desmos, then you absolutely need to put everything in parentheses. Agreed. Okay, so we end up with, instead of 3/2, 5/2, with a coefficient of 2/5. And the same thing over here. Instead of 1/2, we have 3/2 divided by the new exponent. Yeah. Yep. Sorry. Yeah. Yeah. So the new exponent is 5/2. The coefficient is the reciprocal of that. In the second one, the new coefficient is 3/2. So 2/3. But since we already had it 2, 4/3 plus c. All righty. All right. And last but not least, we'll make our u's x minus 1s. So we have 2/5. Honestly, I'm just going to leave it as x minus 1 to the 5/2 power. I don't think it looks any nicer with x minus 1 being raised to the 5th power inside a square root. I don't know. And then plus 4/3 x minus 1 being raised to the 3/2 power plus c. There are some, each one of those could be just the thing being raised to the whole number power with a square root sign around it. But I don't think that adds anything to our problem. All right. That's good. So yeah, the spot on this one, two linear things being two linear arguments at least, like square root of x minus 1 isn't linear, but the argument of the square root function is linear. So two linear things being multiplied or divided, that's your key to do this technique. That's the thing about integrals. You've got to look at the problem and figure out which technique is going to work. All right, number 2. What do we got? X over 2x minus 3. So what's our u going to be? Yep. Our du then is 2 dx. But we don't have 2 dx. We have dx. So we need to. So we're going to have a 1/2 of du in here, dx. Yep. So we can now replace the dx with the orange. We can replace the 2x minus 3 with the blue. We need to solve for x in terms of u. Yep, plus 3 divided by 2. So x, or I guess, yeah, make this equal to x. I'll do this in green. Yep, you're going to add the 3. So we got u plus 3 equals 2x, and then 2x equals, or just plain old x equals u over 2 plus 3 over 2. I'm going to choose to write it that way. That's a u, not a 4. There we go. It does look like a 4. I know. I tried to go over it to make it look less like a 4. Yeah. So that I don't end up with like a full-on complex fraction. I just end up with a kind of complex fraction. I think I like that. We'll see. So yeah, and I'll highlight my x in green. All right. So now this is the integral that we have. Maybe I will like it. Let's feel it out. So we have over u to the 5th, right? All right. Maybe I do like u plus 3 over 2 as one big fraction. Yeah. not u plus 3 over 2. Yeah. So you've got u plus 3 over 2. We can move the 2 down in the denominator. That's what we're going to be able to do there. Yeah, that 2 will go down in the denominator. And my orange. So I need a 1/2, and we need a du. Algebraically equivalent? Yep. The only color coding thing I didn't like was my 5. Came from the problem, not from the work. All right. This is algebraically equivalent to, actually, you know what I can do? Wait. I can just slide that 2 out and make it 1/4. The integral of u plus 3 over u to the 5th du. Which now, because my numerator is a sum and my denominator is just a single term, I can split. So I end up with 1/4 the integral of u over u to the 5th plus 3 over u to the 5th du. Okay. Which, of course, just ends up being 1 over u to the 4th. Okay. And now we have 2 power rule problems. So 1/4, I'll use some parentheses here. Integrate 1 over u to the 4th. My new exponent is u to the negative 3rd, so u cubed in the denominator. And I need to divide by -3, so that's going to be 1 negative 3 u cubed. And then we've got plus, same deal over here. My new denominator is going to be -4. So 3 over 4 u to the -4. Plus c, which now means I have to do the, oh, so yeah, no, sorry, not -4. My bad. Yep, u to the 4th. Yes. And the 3/4 should have been negative because I should have divided by -4. 100% correct. Thank you. Yep. Yes. Divide by -4, so negative out front. Again, I'll distribute the 1/4 in, so I end up with -1 over 16 times 2x minus 3 to the 3rd power minus 3 over 6. Oh, that should be a 12, right? Yep. I was one fraction ahead. 12 here, 16 here, 2x minus 3 to the 4th. You could, but only if it were a multiple choice question, multiply fraction number 1 by 2x minus 3 over 2x minus 3, and then do some coefficient work to get a common denominator. But I do not want to do that. So plus c. Yep. Thank you. All right. Okay. All right. I think that's good. I think there's only 2 more examples left for Monday, right? So that's good. This is something to do. So on Monday, what we'll do is we will work on getting the limits in. The advantage to the limits is they really are just one extra step. It's an easy step to forget. Also, I'll say it here now. But if these things had limits, when we go to u, we just plug both of those limits into the blue, and we change the limits based on that. So if u is 2x minus 3, and in terms of x, I'm going from 0 to 1, I would now be going from 0 minus 3, -3, to 2 minus 3, -1. So you literally, again, algebraically accurate. If u is 2x minus 3, don't put the x limits here. Plug your x's in to figure out what the u limits should be. That's nice because we don't have to do this step right here. And right, we get to jump. We don't have to go back to x's because there's no need to go back to them. Once you change your limits, throw your x to the curb, right? All right. Okay, so 20-ish minutes to become U sub masters.